So remember what we are doing. We are trying to imitate the one variable situation where really, I mean, that's in some ways, that's what we have been doing. Our entire flow is like that. So here what we are doing is trying to see how we can detect local maxima and minima of a function, a real valued function of many variables. So we have the analogous definitions. Uh, a point is called a critical point of a function. So everything is real valued here. We say that something is a critical point if the first derivative vanishes. And remember now that the first derivative is a linear map. So that means the entire map vanishes. For a C1 function, that is equivalent to saying just that the partial derivatives vanish. Or even if the function is differentiable at that point, um, then the partial derivatives vanishing means all other derivatives will be linear combinations. So the entire operator will be. Then the Hessian is just uh, um, the Hessian is just the matrix which encodes all the double partial derivatives. And so we know that if f is a C2 function, then because of equality of mixed partial derivatives, this matrix will be a symmetric matrix. So we call this matrix the Hessian, and we call a critical point to be non-degenerate if the Hessian at that point is non-singular. This is just the analog of, the reason why this notion is relevant is going to one variable situation. So let's see the claims. All right. So we know that so this was one of the most basic theorems, that if the first derivative exists at an interior point where a function has a maximum or a minimum, then the derivative has to vanish. And essentially the same proof goes through just by looking at directional derivatives. But now for the second derivative, we had this following. You see this item number 2. So if I look at a local maximum or a minimum, and so I look at the double derivative over there if it exists, and we saw that the double derivative at a maximum has to be less than or equal to 0 if it exists, and the double derivative at a minimum has to be greater than or equal to 0. So the point is, if I have a critical point and if the first derivative and if the double derivative has a sign, if it is either positive or negative, then then I have the converse as we saw last time, using if the function is C3, because I could use the Taylor series. The point though is that if the double derivative vanishes, then really the test is not conclusive. I cannot really say one way or the other, because double derivative vanishing is compatible with either local maximum or local minimum. And looking at the example of x cube, we know that it need not even be either one of those. So that's the reason why we care in general about this Hessian, which captures the entire double derivative. And the notion of positivity or negativity is whether this operator is positive semi-definite or negative semi-definite. Um, that is the notion of non-negativity or non-positivity. And we saw that by definition, this means that all eigenvalues are non-negative or all eigenvalues are non-positive, respectively, for positive semi-definiteness and negative semi-definiteness. All right, so any questions on this or on anything? Okay, so today what we want to do is we want to in some ways prove a converse to this. That is, so far what we have in both of these items 1 and 2 is that we started with a local maximum or a minimum, and we said what has to be the case with the first derivative and the second derivative. But can we turn this around and we say, okay, uh, the first, at an interior point, if a function has a local maximum or a minimum, then it has to be a critical point. I'm assuming sufficient differentiability everywhere, okay, whatever is required for the, but we will write down a precise statement. So I first identify critical points, and then looking at the double derivative, can I say that this function actually has a minimum or a maximum or neither. Okay. So that's the question that we want to answer today. Remember, we have already answered this question for a one variable situation using uh, Taylor polynomial up to degree 2 and then analyzing the degree 3 correction term. Okay, so let's get started. And this is the result. So as usual, I have a function, a real valued function from open set R in some dimension n, and it is a critical point. And f prime of A is equal to 0. And I'm further going to say that uh, let A be non-degenerate. So what is a non-degenerate critical point? Let's just write down the definition here. The Hessian of the function is non-singular. So then I have the following. Oh, sorry, very
Sir, could you also start the recording?
I will. And I think I have forgotten to put the last couple of classes, so I will remedy that today. Is a and uh, uh, sorry, this is slightly disorganized.
Recording in progress.
Okay, so today we want to detect how a given critical point I can deduce whether it is a local maximum or a local minimum. And so for this, my assumption is now going to be that f is a C3 function, real valued C3 function defined on some open set in Rn. The reason why I want it to be a C3 function is because my test is going to use Taylor approximation. So I need sufficient differentiability for that. All right. And I know that if x equal to A is to be a local maximum or a minimum, then it is necessary that the point must be a critical point. So I have to require f prime of A to be 0. And my second derivative test is going to fail if the second derivative is singular. So I assume that the Hessian matrix, which puts together all the double derivatives, is a non-singular matrix. So then I call such critical points to be non-degenerate. So then I get to say the following. So this is the claim. Uh, we already saw the one variable version, so I will not repeat it. F has if and only if H is a positive definite symmetric matrix. Remember, the matrix has to be symmetric because the function is C3, in particular it is C2. And it has a local maximum at A if and only if H is negative definite. Remember, positive definite simply means that all eigenvalues are positive, and negative definite means all the eigenvalues are negative. So does a non-singular symmetric matrix have to be positive definite or negative definite? No, it's certainly not necessary that see, I'm given that all eigenvalues are non-zero because the matrix is non-singular. But it may very well happen that some eigenvalues are positive and some eigenvalues are negative. And in that case, what we can say is that F will have neither a local maximum nor a local minimum, but it has a saddle point. F So of course, I have to define what a saddle point is. Uh, when H is indefinite. So let me just write down recall definitions here. A critical point is called non-degenerate if the Hessian is non-singular at that point. What else? Yeah, so index of a non-degenerate critical point
Hello, sir.
is, yes, go ahead, please.
Sir, if H is indefinite, then we cannot say whether it is a local max or minimum, right?
No, in fact, what we can say is that it will be neither a local maximum nor a local minimum, because look at the double implications.
Oh,
Those
yes, sir, I
implications
see.
are if and only, right?
Yes.
And in fact, we will see what happens. I drew this picture at the end of the last class after the class finished, but we will see it. Okay. So index of a non-degenerate critical point is just a uh, non-degenerate critical point, let's call A, is sigma of A, which is by definition the number of negative eigenvalues of the Hessian of the function at A. So what will happen? If the operator is positive definite, then the index is zero. If H is negative definite, then the index will be N, and anything in between, we call it is going to be indefinite. And this is kind of a cop-out definition. When That's what we call a saddle point. We say that the uh, that of course this is non-degenerate critical point is a saddle point. Okay, so we will come to the this saddle point business at the end, but first let's take care of what happens when uh, when we actually have positive definiteness or negative definiteness. So proof of the theorem. Proof of the theorem. And you know what? We imitate exactly what we did in the one variable situation. So let's write down Taylor's theorem. So by Taylor's theorem, what do we get to write? f of a plus. Now I don't want to use small h because I have capital H, which is the Hessian. So let's use x minus f of a. What is that equal to? So I have simply taken the f of a term to be on the other side. So so this is going to be f prime of a times x, right? But f prime of a is 0. So let's write this down, f prime of ax, but that is 0. What is the next term? So we worked this out yesterday, and we've done it earlier also. So the next term is half times.
So f double dash a
Right, f double
x
dash
square.
a. And when so f double dash a, so you're thinking of the one variable situation, and then it would be f double dash of a times x square. When I interpret this in the multivariable situation, I regard f double prime of a as
As
a
an operator.
as an operator, but an operator which I regard it as a bilinear map from Rn cross Rn to R. And I'm evaluating this on the vector x comma x because it's from Rn cross Rn to R, right? But then we worked this out, and then we saw that this really is the matrix multiplication when I put x transpose on this side times h times x, right? And what is the remainder term? So let's call it R of x with the exact form of the remainder term I do not need, but what I know is that with R of x by norm of x. So in fact, what do I get to put in the denominator? It's as stated, this is wrong. So what power of the norm of x in the denominator? Okay, so just think of the one variable situation. This is a degree 3 term, right? So there is something or the other that I can bound times the third power of x. And so this will go to 0 even if I divide it by x square. So this is what I have. All right. Um, so by Taylor's. So first let's assume that H is positive definite. So what does that mean? All eigenvalues are all eigenvalues are strictly positive. And so what did we see as a result about this quantity? This x transpose hx.
It is strictly greater than 0.
As long as x is
Non-zero.
as long as x is non-zero. And by the way, we can see this one. We can see this. How did we see this? We can just plug in x as a linear combination of all of the eigenvectors, and then notice what happens. For example, if x is an eigenvector, let's say with positive eigenvalue lambda, then that hx is just lambda x. So the h disappears and I get a positive factor lambda multiplied by x transpose times x. Now x transpose times x is just the sum of squares of the components of x. So I will get lambda, which is positive, times something that is positive because x is non-zero. And in general, I just take a linear combination of such calculations. So I know that this quantity is positive. So all that I have to do is to show that, notice what do I want to show? I want to show that at A, I have a local minimum. That means that for all small values of x in all directions, the left hand side has to be, I want to show that f of A is a minimum. That means that for all small values of x, small non-zero values of x, f of a plus x must be greater than or equal to f of a. Right? So I need to show that the quantity on the left hand side must be greater than or equal to 0, which just means that this quantity that I had just highlighted, I know that that is positive. So as long as I show that the remainder term does not beat that in an entire small neighborhood, I'm done. But that's exactly what this last business is going to do. So let's prove this. H is positive definite. So for x not equal to 0, x transpose hx is strictly greater than 0. Now the issue though is that if as x becomes small, this quantity, even though it is positive, it could go to 0. And in fact, it will, no? Because you see, this quantity has x as a factor in there, right? However, the point is that this quantity divided by the norm of x square is something that has a lower bound. So why is that? So in fact, uh, so this is what my claim is, that x transpose hx divided by norm of x square is greater than some quantity, is greater than or equal to some mu for any x not equal to 0. So can you see where this is coming from? So we did something like this before. So essentially this quantity that I have written, that has, so that has, if I scale x on both sides, then let's say I keep taking x smaller and smaller, then the quantity x transpose hx will become smaller. But the effect of scaling I have negated by dividing by the norm of x the whole square. So do you recall something of this nature that we did earlier, where we tried to somehow get a single number that captured how big or small an operator can scale something to become?
In operator norm.
And we are going to do exactly the same thing over here. So over there, what we considered was, we considered the function, the operator times a unit vector. Here we will do the same thing when we take unit vectors, but we will consider the new function. So x goes to x transpose hx is continuous. So it's going to be a quadratic function, right? If I just write everything in terms of coordinates, this h is just a matrix of constants. So it's going to be a quadratic function. So on the set u such that norm of u equal to 1, it takes so on the set. So what kind of set is this? The set of all unit vectors is, it's a compact set. Right, it is a closed set and it is a bounded set, and we are working in Rn, so it is compact. Therefore, I'm applying this continuous function to a compact set. Therefore, the image is going to be compact, right? And therefore, it is going to be closed and bounded. So it is going to have a supremum and an infimum, and it is also going to attain those values, right? In case of operator norm, I was really concerned with the maximum value that would take. Here, I'm more interested in the minimum value that it will take. So it, so now I'll say the function is continuous. So on this compact set, it will achieve a maximum, and it takes, it is bounded, achieves its supremum and infimum, but here actually I'm going to take infimum, and that infimum I'm going to call, of course, mu. What do I know about mu? I mean, mu is an infimum of a function that takes only positive values. As such, the infimum has to be either positive or zero, right? Because infimum of positive numbers could be zero.
Being
But the
compact,
point
it will be
is that
positive.
it actually takes the infimum, right? Right. So therefore, and achieves its infimum mu. So mu is greater than zero. So all right. So this is okay. So I have this fact. Now do you see why this is going to happen? So what happens is that the infimum was obtained on only the set of unit vectors. But this is precisely equal to x by norm of x, the whole transpose times h times x by x, x, correct? So this is a particular instance of the set over which I have taken the infimum. So, so this all works out. And do you now see how to complete the proof? I complete the proof exactly the way I did it in the one variable situation. So can you tell me now what to do? Well, I know that this quantity over here, this quantity, no matter what x I take, that quantity divided by the norm of x square is bounded below by, let's say, mu divided by 2. And I know that the remainder divided by norm of x the whole square, that is something that um, goes to 0. So I can just choose x close enough so that the first quantity always beats the correction term. So let's write this down. Uh, um, since the remainder divided by norm of x the whole square goes to 0, as norm of x goes to 0, we can find, let's just do the sort of usual epsilon delta thing. We can find delta greater than 0 such that this quantity r of x divided by norm of x whole square, well, its absolute value is less than, uh, let's say, what, mu by 2 when norm of x is less than delta. So as a result, what happens? Thus, for whenever x is less than delta, what do we get? We have f of a plus x minus f of a. Remember, which is equal to what quantity? The quantity that I have just bounded, that I have shown to be since I have chosen x small enough so that, oops, okay, so that this term always dominates that term, I know that the sum of these two terms cannot be, has to be non-negative. Okay, let me just write this. I.e., f has a local minimum at E. Okay, and of course, in the other case, so let us see what the claim was. I have assumed that H is positive definite, and then F has a local minimum at A. How about the other way around? If F has a local minimum at A, do we need to prove that H is positive definite? Well, okay, no answer. How about the forward direction? Suppose F has a local minimum at A. Do we still need to prove that H is positive definite? Okay, so maybe I'm not really making sense. Is this really unclear? What did we prove in the last class? We said that at a critical point, the derivative has to vanish. At a local maximum or minimum, the derivative has to vanish. And at a local maximum or a minimum, respectively, the double derivative has to be uh, negative semi-definite or positive semi-definite. So the only point here is that the semi is dropped. But that is by hypothesis, no? Because I'm taking a non-singular critical point. I'm assuming that the Hessian is non-singular. So I have already ruled out by hypothesis H having zero eigenvalue. And we already proved last time that if you have a local minimum, then the Hessian has to be negative semi-definite. If it has a local minimum, then the Hessian has to be positive semi-definite. So by hypothesis, now it has to be positive definite because I assume that zero is not an eigenvalue. All right, let's. Okay. We already proved that at a local minimum, H is positive semi-definite all eigenvalues are greater than or equal to 0. But we assumed that H is non-singular. So all eigenvalues are non-zero. Hence, they are all positive. Okay. And um, for local maximum statement, just apply the above to minus of f. Correct? Because everything will just become minus of what it was. All right. So are there any questions so far? Okay, so in that case, I have some questions because I do not quite like the quality of silence today. So let me ask you, Is it so? Why is it that in case of a local maximum, or let's just say a local minimum, what was the reason for this statement? So why was this the case? We already proved that. Can you tell me why? Was this a mystery? Did it require serious proof, or was it something easy? That if I have a local minimum at a point A, then the Hessian has to be positive semi-definite. Why? Okay, so recall why. And let's do this another way. So suppose, so there is this Hessian, right? And I want to show that it is positive semi-definite. What does that mean? That means that every eigenvalue is non-negative. So let lambda be an eigenvalue. What was our basic calculation? So let's recall that. So want to show that lambda is greater than or equal to 0. What is it that we know about the double derivative? And we fall back as usual to the one variable situation. We know that if I have a local maximum for a one variable function, a local minimum for a one variable function, uh, and if the double derivative is defined over there, we know that that has to be non-negative, right? So how did that become applicable here? So how do I connect this eigenvalue lambda to the double derivative in the one variable situation? What do I do?
Sir, consider the directional derivative along
Exactly, right? Along
the eigenvector, which
the
is
eigenvector. So eigenvalue of h with e vector u. In that case, there was a sort of fundamental thing, right? So what was d sub u square? So we want to consider, so basically we are restricting the curve only along this direction. So now I have a one variable situation. If you want, what the way we do it formally is that we pre-compose the function and we put a line. So let t go to a plus t times u, and we take the composed function, and now this composed function will have a minimum at t equal to 0. Okay, so I can check. So I know that the double derivative therefore has to be greater than or equal to 0. But what is this double derivative? So d sub u square of f at a was what? Basic calculation. So we did this calculation. What did this work out to be? Hmm. No, do not remember this.
Like if we write u in terms of the standard basis,
Correct.
and then like it just turns out to be a linear combination of
Right, but we sort of did this entire calculation, and what was the upshot? We did have an end result.
like this was just the bilinear form applied to that vector,
Correct.
where the bilinear form is the Hessian matrix.
Right. So exactly u transpose times h times, oops, sorry, not a, times u. Okay, but I have taken u to be an eigenvector with eigenvalue lambda. So what does this work out to be?
Lambda u transpose u.
Correct. So h times u becomes lambda times u. Lambda is a scalar, so it moves everywhere. So this is lambda times u transpose times u. U is an eigenvector. In particular, it's non-zero. So u transpose times u is a positive quantity. right? It's just the sum of squares of the components of U. And I know that this, by one variable calculus, I know that this is greater than or equal to 0. And this is greater than 0. So the upshot is lambda is greater than or equal to 0. Okay. So the proof finished here, but this is the recollection. With this in mind, we can now go back and revisit this saddle point business. So, meaning of saddle points. So let us see what we have achieved here. Among the three statements, we proved the backward direction of the first statement. That was where the new proof was required today using Taylor's theorem. The forward direction was something that we had done earlier. Okay. So this is statement number, so let's say 1, 2, and 3. Now 3 is more or less definition, but we have proved number 1, and number 2 was really just the same as statement number 1. You just applied to minus it. So let us see what the meaning of this saddle point is. And the saddle point is when, let's recall the definition. Saddle point is when the Hessian is non-degenerate. In other words, you can think of it as the double derivative being non-zero. However, not all eigenvalues are positive and not all of them are negative. Remember, none of them is zero because I have taken H to be a non-singular operator, right? So that means that at least one eigenvalue is positive and at least one eigenvalue is negative. So now just look at this calculation over here. What does this say? That means that I have one eigenvector, let's say U1, with corresponding eigenvalue lambda 1 that is strictly positive. What does this mean? This means if I restrict this function in the direction of this vector U1, what do I see at A?
In that direction, it will be a local number.
It will be a local minimum because the eigenvalue is strictly positive. That means that the second partial derivative in the U direction, that is du of f at A, is a positive number. And we know that in that case, in that case, I have a local minimum over there. However, if I go in the direction of a second eigenvector U2 with a negative eigenvalue lambda 2, then I know that by the exact same logic, in that direction at the point A, I have a local maximum. So this is a new phenomenon, something that you do not see in one variable situation. So let me write that down. Meaning of saddle point. In this case, in this case, at a non-degenerate critical point A, I have, by definition, not I have. H has both a positive eigenvalue, say lambda 1 with eigenvector U1, and a negative eigenvalue, say lambda 2 with eigenvector U. But this means du1 square of f at A is going to be greater than 0, and du2 square f at A is less than 0. So in the u1 direction, f has a local minimum, and in the u2 direction, f has a local maximum. So this is the situation that
Sir, in U1 direction, it has local minimum, means along that line itself, right? We are considering the neighborhood.
that's all, right?
Okay.
Uh, yeah, and that probably is a better way to say that if I slice the function. So let me see if I can draw the picture from yesterday. Uh, so this is the graph of f, and I have, let's say, so this direction. So I have a local minimum. So I'm going from, so this is a 3D picture, right? I'm just looking at the profile of a mountain, but actually the picture has depth. And so where do I have the local minimum? In the U1 direction. And in the U2 direction, I have, so that is, imagine that I'm crossing this, I'm crossing from one side of this to another side. So that is the U2 direction. I have a local maximum. So this is the point A is over here. So this is the point A. Okay, so I hope the picture is clear. This is a function of two variables. Uh, so this is a function y equal to f, oh no, not y, z equals f of x comma y. And in the plane, I have just chosen two directions. And the z axis is over here. So z is the vertical. Okay, so any questions so far? All right, so now life becomes interesting because now I get to do lots and lots of examples. And we'll just proceed systematically. So one thing to keep in mind, we have all these careful hypotheses. If f has a derivative, then that is enough to say that an interior point will be a local maximum or minimum. Then the derivative has to be 0, etc., etc. And then for the Hessian, uh, in order for to assure that all the eigenvalues are real, we have to take a C2. We take a C2 function to ensure that the matrix is symmetric. And then finally, we take a C3 function in order to apply Taylor's theorem. But in practice, for many, many functions, polynomial functions, exponential, and things that are built out of these using composition or the four arithmetic operations, these functions are going to be differentiable, even continuously differentiable wherever they are defined. And I even have formulas for their derivatives, which is just the matrix of their partial derivatives. So in practice, many times, all of these hypotheses, they're just automatic. Right? So let's start with very easy functions. That is, what happens if I take, what happens, so many times, I don't want to say most of the times because that maybe depends on the context, but many times or even C infinity wherever defined. So all of the above applies. Uh, so let's look at polynomial functions. Right? Polynomial, real valued polynomial functions of several variables. So the simplest case is constant. So f of, and let's just take two variables, f of xy equals c, constant. So in all of these cases, this is, I mean, nothing much to say, and f of xy is a linear function. So ax plus by plus c. So what happens in these cases? What happens in the first case? Well, all the derivatives are zero. So everything is a critical point. What about the Hessian? Come on. The Hessian is the zero matrix. Everything is zero, right? So does the theorem apply? I mean, never mind that we know exactly what this function is, but the theorem does not apply because the Hessian is not non-singular, right? It's the zero matrix. But nonetheless, there is nothing much to say about this function. Every point is a local maximum. Every point is a local minimum, global minimum, maximum, everything. Okay. What about for the linear function?
The Hessian is again 0.
Hessian is zero, but what about critical points? And let us assume that linear is actually linear in the sense that A and B are not both zero. So what happens? How many critical points do I have over here?
We don't have.
Yeah, we don't have. I mean, how can the derivative is the matrix A comma B? And I just said that it is not both zero. So no critical points. But you also know, right, this function does not have any maximum or a minimum. Right? It will just go off to infinity. So the interesting case starts when I have a quadratic function. So f of x comma y is equal to a quadratic. Okay. So we could do the general analysis, but maybe what we can do is we will just, I'll just give you an example. Okay, how are we on time? Oh, we don't have a whole lot of time. So let's do the general analysis. So general case. Let's see the general case. And here's what we have. And I'm following Professor Pramad's notation. So I'll follow his general case. So let's call this phi of x, right? And now x is a vector. X is in Rn. Okay, so x is a vector. So it has components x1 up to xn. So this is going to be x1 up to xn. And maybe you can take the transpose of this regarded as a matrix. But anyway, so what is it going to be? There is going to be the quadratic part. That means all of the variables xi, they will be squared and they will be sum term. Then there will be some cross terms, xi, xj, that such terms will have some coefficients. Then there will be a lower degree part, which is linear part, exactly like what I have written above, plus a constant. So let's set up notation. So this is going to be summation aii xi square, I going from 1 to n, plus summation aij xi xj. And so what should be the indices over here? I and j should not be arbitrary, because then I will should not independently go from 1 to n, because then I will get aij and aji. but I really want to count xi, xj only once. Doesn't matter, no, if I write, say it as x1, x3 and x3, x1. So the way I do it is, I say I less than j, and both between 1 and n. So 1 less than or equal to I less than j less than or equal to n. And then for some reason, I normalize this in such a way that I call this coefficient 2 times aij. Okay? You will see the reason for this because something becomes nicer. And then plus I have a linear part. So plus some pi xi plus some constant. And what is that called? It's called r. So this is I going from 1 to n. Okay, so let's quickly just write down what, do the analysis, critical points, etc. And it will be nicer if we write this function in the matrix notation. So just notice the following. This is the same thing as x transpose times A times x. Plus P times x plus R. So where, let's write this down. Let's just write this out so that it is easy to see. Notice, so this x transpose, this is just the vector x1 up to xn, correct? Now A is going to be a11, a12 up to a1n, an1 up to ann, and times the vector x1 up to xn. Can you tell me where the 2 went? Yeah, so you see the point is, one, the way I have defined it is not quite well defined because you see only a12 is defined, a21 is not defined. But of course, I do this in such a way that a12 is the same as a21. And in that case, you see every term aij, xi, xj, that comes once, and aji, xj, xi, that comes once. So when I add those together, that's when I get 2 times the term. But of course, for the terms diagonally, the 2 does not come. So you see this matrix notation sort of is telling you why I put that 2 in there. Okay, so where aij equals aji. Okay, and then what about the p and x? So again, this is the same thing. I think of p1 up to pn times x1 up to xn, and then r is just a real number. Okay, so this is how it is in shorthand. So just do the calculation now. What is the critical, I mean, are there any critical points and what is the Hessian? So in order to find the critical points, what should I do? I need to calculate the first derivative. No? So what is di of phi at x? Just do the calculation. And again, the virtue of 2 will sort of become clear. So in the first terms, the only things that are, the only one of the terms is going to survive, where, where the index I, that is going to survive. So I will get 2 times aii times xi, right? And from the second one, what will happen? Out of the n choose 2
in
terms.
either of them, if I is present.
Correct. But remember, each xi, xj is counted only once. So out of the n choose 2 terms, exactly n minus 1 will survive. So I can combine the first and the second, the first term from the first n, one of the terms from the first n terms, and n minus 1 terms from the n choose 2 terms. And both of those will have 2 as a coefficient. So what do I get altogether? 2 times summation aij times xj, j going from 1 to n. Just pause. This is a simple calculation. And what else is there? Plus come on, what is left? What else is there? From the linear term, I'm going to get a contribution, right? So I'm just going to get plus pi. Okay. So this is really the same thing as saying, okay, so this is 2 times the matrix A times the vector X. Yeah. And then plus the vector P. Maybe I should write P transpose, but okay. So I'm going to say, so this is equal to 2 times Aij, this matrix times x1 up to xn plus, oh, sorry. Uh, not this. This is only for the di, right? On the other hand, I'm going to say therefore d of, yeah, my bad, d of phi at x is this one, which really is equal to 1 to p. The total derivative, and that is just this. Okay, so how many critical points are there? So critical points x such that 2ax plus p is equal to 0. Right? So that means I need to solve a linear equation. That is 2a times x equals minus p. How many solutions does such a thing have? Well, that kind of depends. No? A general linear system will have, by the way, what is the size of the matrix A?
N cross N.
It's n by n, right? So if this matrix is non-singular,
So then it has exactly one solution.
then it has exactly one solution. But if it's not non-singular, then it kind of depends, right? It
may
might have no
zero,
solution.
it may have infinitely many.
Right, exactly. Yeah, right, exactly. But let's take a look. Let's put this on the back burner and you will see that we will come back to this. What is the Hessian? So in order to do that, I have to calculate di dj of phi at x. No? What is that? Just calculate for a moment and then you will see what's going on. I have already written the d. I have already written the di up there. Or maybe, yeah, so just calculate and see what happens. Maybe I should write it dj di. So
Yeah,
that you can, exactly, you see. So, but not aij, but because you see the 2 has come down already. So what is that? Okay, just see what is going to happen. If I apply d1 twice, what happens? The linear term is just going to die, correct? Because I'm taking second derivative. Of course, constant was dead the first time around. And you see, if I apply d1 twice, then the only term that will survive is the x1 is the x1 square term. You have to have x1, right? In order to, if there is no x1, then it's a constant. So the derivative will die. And in order to take the d1 twice and still have it live, the only term that will survive is x1 square. And that will give me 2 times a11. And likewise for d2 square, etc. But in exactly the same way, if I have to take d12, then when I first apply d2, only the terms that have x2 will survive. But after that, I have to have a term that has an x1 in there. So the only thing that is going to happen is that the x1 term will x1 x2 term will survive, and its coefficient is a12, which is the same as a21. So this is going to be 2 times aij or aji. So you see this matrix. So H is really equal to 2 times A. So when we see this up here, 2A equal to H is assumed to be non-singular, right? So okay, so let's say if it is, if I didn't make that assumption, so if then there is a unique critical point, namely x equals what? I have to
So
multiply
half
by
of
H.
A inverse P minus P.
Right. But I will not write A because I will write it in terms of the Hessian, and H is just 2 times A. So H inverse applied to minus P, so minus of H inverse of P. Okay, so that's the situation that I have. And then I know exactly what happens, which is to say that if H is non-singular, if H is non-singular, then the unique critical point A is equal to minus H inverse of P is local minimum if, local maximum if, and saddle point if. So we can just say if H is positive definite, H is negative definite, and otherwise. I mean, the issue here is that the Hessian can be just, so note that, so I'll just say H can be calculated or can be written down just by looking at the equation. Formula for phi, and depends only on the quadratic part. That is the homogeneous quadratic part. You see, notice that H turned out to be 2 times A, but look at where A came from. That was just the matrix of coefficients of the degree 2 terms. So you can just get it from there. Okay. So, all right. So examples of this. So we're almost out of time. Let me write down some examples of this. So you should calculate all of these. Calculate critical points, Hessian, local max, min. And the key thing is, and visualize. So there is a lot of geometry going on over here. Let me just write down some very basic examples, and I will also give you references. So visualize. So f of xy equals a bunch of things. Let's say x square Then we can do x square plus y square. Then of course you can do minus of x square plus y square. Then we can do x square minus y square. We can do xy. So I have not put any kind of linear term over here. So these are very basic examples, and several more. So I'll just give you a reference because we are out of time, but we will do these in class or similar examples, and several more. For example, see Professor Pramad's lectures. Lectures 15 and 17. But we will do these in class also. So let's stop for today and we will continue next time.
Recording stopped.
And one thing that I forgot to say, but we will do this next time, which is draw contour diagrams, or what we call level sets. So there is a lot of geometry here. There is a lot of geometry to see and appreciate. For example, draw level sets. In geography, you call those contour diagrams, and visualize gradients. Visualize gradients and the nature of the surface. Because when I plot this in 3 dimensions, then the input is going to be an x and y axis, and the vertical z axis will show you the height. So this is really something that one should do for oneself. If you want, we can do some of the examples now, but maybe, and I'm happy to do that, but maybe this is something that that really everybody should do for themselves. Maybe what I'll do is I'll give you one of the examples that such as of course, as a calculation, you can do these calculations, but one sort of key thing. Okay, let's just look at these 2 examples. Look at these examples: x square minus y square and xy. Let's just think of them for a moment. How many critical points do we have? Let's look at x square minus y square. How many critical points?
Just one. 0,
Just one. Where? At the origin, correct? All right. What's the Hessian? Remember, the Hessian is going to be a constant matrix, and you can look at the recipe that we have given above, or you can do it by hand. It's really the same. Not much work. So what is the Hessian?
Just 1 minus 1 along the diagonal.
Yeah, actually 2 and -2, correct?
Yeah, 2.
Not that it matters. Okay, so 2 and -2. So what kind of critical point do I have there?
Saddle point.
A saddle point. Okay, so good. And in fact, so you can see uh, in uh, in which direction if I travel, I have a maximum, and in which direction if I travel, I have a minimum. You can see this. All right. So just visualize for yourself. If you draw the if you draw the if you draw the level sets of this, level sets means that you simply take the function and you fix a certain value of z, and you see all the x and y such that that equation is true, and you just draw that as a curve in the xy plane itself, exactly the way when you draw maps. On maps you have these elevations given as contour lines, right? I hope everybody has seen this in school. So this is interesting. What is the most interesting contour line? Of course, the one that passes through the origin. So at the origin, the value of this function is 0, x square minus y square equal to 0. What is the graph of that? Come on, x square minus y square equal to 0. If I draw the graph of that in the plane, what do I get?
It's two lines, like one is for x is equal
X
to
equals y and x equals minus. Okay, good. And then you will see that the rest of the contour diagrams will either be hyperbolas that open to the left and right, or up and down, depending on what level we have. Okay. Okay, very good. Let's now go to the last one, xy. What about that? So partial derivative with respect to x, it is y. With respect to y, it is x. So that's the matrix, y and x. For this to vanish, again, x and y both have to vanish.
It will have a
So
minimum.
again,
I
only
mean,
the
the Hessian is 1 along the diagonals.
no, just check carefully. Is it 1 along the diagonals? In fact, what is the Hessian along the diagonals? That means I have to take the partial with respect to x and then again partial with respect to x. What do I get? For xy.
It's 0.
Right. And likewise, partial with respect to y done twice, that is also 0. However, the Hessian is non-singular, because what are the other two partials, the mixed ones? I have to calculate just one of them. So what is it?
They are ones.
They are both 1, correct? If I calculate partial with respect to x, I get y, and then I take partial with respect to y of that, and I get 1. So the matrix is zeros along the diagonal and ones along the skew diagonal. Okay. All right. So, so what kind of matrix is this? Is this positive definite, negative definite, neither? As a linear transformation, what is this? 0, 1, 1, 0. What does it
It's
do?
just the exchange matrix.
So it exchanges x and y coordinates. But that precisely means it's a reflection. In which line?
So x equal to y.
The reflection in x equal to y. So what kind of, so is this positive definite or negative definite or neither? What are its eigenvalues?
One and minus one.
1 and -1. So I again came to the previous situation. And now here is the reason why I wanted to do this. Coming to the geometry of this, which is they just look different. They're exactly the same functions. I mean, not identical, but do you see that the graph of x square minus y square and the graph of xy, they really are the same graphs up to scaling. Up to scaling and
rotation.
yeah, exactly. Because if I put a new coordinate, if I call u to be x plus y and v to be x minus y, then that x square minus y square is really just u times v, correct? So in the new coordinate, it really is the same graph as before.
So this is actually just substituting along the mirror and perpendicular to the mirror. I mean, the
Right.
x
So
plus y and x minus y.
in this case, the way I have done so I have just reparameterized this, but the reparameterization is also in a nice way, in the sense that I'm doing this, I'm keeping the angles the same, right? So it's just a rotation. Okay. So the original axis I rotated to give me new axis, and in terms of the new axis, and I have to scale the new axis appropriately. Maybe I have to put a half or two somewhere, depending on how I'm doing it. The old equation with respect to new coordinates will become the other equation. The shape is not going to, this is like you're seeing the same mountain, you're just standing in a different place. Okay. So the details of the calculation may change, but it really is the geometrically it's the same phenomenon. And so here the change of coordinates is only linear, but we can make other changes of coordinates. And we will get to this more general thing when we come to inverse and implicit function theorems. But right now, the change of coordinates, you can say simple changes of coordinates. That is what you saw in school, right? You can just shift. If you just shift the origin somewhere, then just x and y will just get shifted by some whatever plus minus things. The equation will look different. Right? See that. So for example, this x square plus y square, what is that graph going to be? Forget doing the Hessian, etc. Can you just see how the graph is going to be? If you draw the level sets, then you will see what's going on. If I take particular fixed values of x square plus y square, then the lowest one has to be 0, and I'll get only a point. And otherwise, I will get expanding circles at higher and higher levels. Now, if I shift those circles along the y-axis to their whatever level they're supposed to be, then I'm going to get the graph. So how will the graph look like? Yeah, the graph of x square plus y square. No, so okay. What happens if I cut this graph along one of the if I just say I just set y equal to 0, I look at only the values of this function when y is equal to 0. Then what is the graph? What is z then? Z is just x square, no? So now, which is a parabola. So can you imagine how I should think of this graph in terms of this parabola? I'm just going to take this parabola, which is in the xz plane, and I can do something to it to get the entire graph.
We can just rotate about the z-axis.
Just rotate it, right? We can rotate it around the z-axis, correct? I'm picturing xy axis as in the plane horizontal and z as the height. So in this case, it is clear that there is going to be exactly one critical point at the origin, and the minimum value is 0. And the next one, when I take negative of this, it is just the same thing flipped upside down. So again, you can see what the Hessian is going to be over here. For x square minus y square, I got 2 and minus 2 along the diagonal. In this case, I'm going to get 2 and 2 along the diagonal. So this will be a positive definite. And correspondingly, I got a minimum. Imagine now that I do the following. All right. This x square and y square, I simply I just put in some x plus k and y plus L into that for x and y. Then you see now it will get smeared because I'm shifting the center somewhere. You can also just sort of imagine that this entire thing I'm just going to take and sort of tilt it slightly. Geometrically, it is not going to change the nature of it, but the equation will become something quite different. All right. So how about x square? What kind of Hessian do I have for that? Well, so the only the double partial derivative, del by del x, del by del x, that is the only one that is going to survive and going to give me 2. All the other entries are 0. In other words, what kind of Hessian did I get? So does the theorem apply in this situation? And the answer is no, because
But
this Hessian matrix is singular, right?
yes.
It's, so Hessian matrix is singular. Nonetheless, so what kind of graph am I going to get for this? Yeah, f of xy equals x square. What kind of graph am I going to get? How many critical points? Or rather, where are the critical points? There are lots of them here.
The whole y-axis will be critical point.
The entire y-axis is going to be, and can we classify those critical points? Looking at the picture. I mean, just see, no, when x is 0, this function is 0, and otherwise it is going to be positive. So all of these are minima. In fact, they're all global minima, particular local minima, but there is a whole line worth of them. And the graph is, there is no mystery about the graph. You just take x. I mean, it's like taking a sheet and just bending it in the shape of a parabola so that the profile is a parabola. But our test does not tell us that, because the Hessian is singular. So really, so what is going on? It is exactly like the one variable situation, with the following exception. If the Hessian is singular, then again the test fails, and anything can happen. Because we can just go to the one variable situation, right? We have x square or minus of x, the Hessian is, we have x to the 4 or minus of x to the 4 or x cube. So it could be a local maximum, it could be a local minimum, or it could be neither. So it's exactly the same thing happens over in that we cannot tell anything. But the phenomenon is now richer over here, in that even if the Hessian is singular, even if the Hessian is non-singular, which is to say, I mean, you can think of this as, oh, the double derivative is non-zero. That is, it's an invertible operator. Even in that case, you could have a maximum, you could have a minimum, or you could have a saddle point, because there may be different behavior in different directions. In these eigen directions for the Hessian, you will have either a maximum or a minimum, either a local maximum or a local minimum in each one of these directions, because the eigenvalues are positive or negative, correct? It is just that if all of them are positive, that then and only then will you have the eigenvalues, all of them. it's a very useful and important thing to visualize some of these graphs, even the simple ones. You see, the reason why I gave these to you is they're very simple, uh, and in the quadratic case you don't really have any much more than this, because of the principal axis theorem, which I will see, which we will see in class. But it really is just manipulation. Basically, you're saying that you can shift the origin and you can sort of change the axis in such a way by rotating that it will come to a standard form. That's just algebra. So let me see if I can show you some pictures in class with some suitable software. But anyway, one has to learn to visualize this on one's own to gain some geometric intuition, and not just sort of do this formula, that formula, and get something out. So we'll continue with examples on Monday. Anything else? Okay, good. So let's stop for today and continue on Monday.